Hi guys, and welcome to another HSC Chemistry video in the acidic environment video series. Now this one's on acid-base equilibrium, and there's a couple of things that I've put in here to try and help you understand some things, even though you don't specifically need necessarily to recall this information in your exam. This you do. We know now that the quality of strength of acids is based on their degree of ionization. We now know that many acids only partially ionize in water, while some will go to completion. The stronger the acid, the more readily it is ionized. So the strongest acids are the ones that are completely ionized, and the weak acids are the ones that are only less well ionized. In one of the previous videos, for example, we had a look at the fact that acetic acid, in one of our examples, only ionized by about 1.26%. That is, over 98% of the original acetic acid molecules remained intact. So that means that we can write the process of ionization of acids as an equilibrium. This equilibrium means that sometimes the equilibrium will lie, the position of equilibrium may lie to the left for a very weak acid and will lie to the right for a very strong acid. Okay, and that just is a measure of the relative concentration of either the HA or the H plus and the A minus species. Remembering, of course, that we use HA to represent the acid, H plus are the ions that are produced when it ionizes, and A minus are the anions that are left behind once the hydrogen ion or proton has left. Remembering too that we often have another part to this which we haven't shown, which is the water molecule itself participating, meaning that the H plus ion is actually in the form of an H3O plus ion. Now, the extent to which acids are ionized can be determined using a specific equilibrium constant, which is known as the acid ionization constant, or Ka. Now, one of the things that's really important about this section is you do not need to remember nor perform calculations with the acid equilibrium constant. We will go into this constant in a little more detail when we look at industrial chemistry, but the only reason I'm raising it now is because it may help you understand some of the concepts behind why some acids are regarded as strong acids and others as weak. If you already understand those concepts, if you feel you've got a good grasp on why that's the case, then you may not need to go any further in this video. But if you want a little bit more background as to why, then let's have a look at one more slide. So this is the way we calculate the acid equilibrium constant. So what we do is we multiply the concentration of H plus ions by the concentration of A minus ions, and we divide that by the concentration of the HA. Now, if you think about something that fully ionizes, that is the, so for a strong acid that is fully ionized, the concentration of HA approaches 0. And that means the Ka value approaches infinity. And if the Ka value approaches infinity, then we don't have an equilibrium. Okay, there is no equilibrium if the concentration of the original reactant is 0. So as the original concentration approaches 0, Ka approaches infinity, and we do not have an equilibrium. Of course, if the value of the Ka in the HA increases, so as this increases, we have less and less of the H plus and the A minus, and this means that our Ka value, as the denominator is getting bigger, the Ka is getting smaller. So it will approach 0 in this case. If the HA were not to ionize at all, that means if the concentration of these two were approaching zero, then we would not. Then we would just have a Ka which equals to zero, and that means that we have no equilibrium at all. There's no reaction, nothing's happening. So between these two extremes, we have a Ka value which is very, very low, which means that very little is ionized, or we have a Ka that's very high, and that means that most of that acid is ionized and there's only a small amount of the original molecule remaining in the solution. This equation gets a little bit more complicated if the acid is not monoprotic or diprotic, because what we will generally need to do is to raise the power of the H plus to either a 2 for a diprotic or a 3 for a triprotic, and it becomes a little bit more complex. And as I said, you don't have to use this. It's not a mathematical equation you need to use. It's a conceptual thing that just tells us how does this particular value change as this goes up and these come down, or as this comes down and these go up. So if you can understand that, then you'll get a little bit of a sense of what happens with the ionization of weak acids with water. Thanks for watching.